Good day to our lecturer and fellow classmates. My name is Awangko Faris bin AK Sabri, and today my group will be presenting our scientific literature critique on the paper titled Experimental Investigation and Optimization of Reclaimed Sand Casting Parameters for the Aluminum Alloy Casting Process, authored by Yoshino and colleagues, published in 2026. Okay, so to give some background, sand casting is one of the most widely used manufacturing process for complex metal parts in foundries. However, continuously disposing of spent foundry sand creates severe environmental pollution and drives up production costs. While reclaiming and reconditioning waste sand offers a sustainable solution, improper sand preparation introduces critical casting defects such as porosity, blow holes, and shrinkage cavities. Therefore, the main objective of this study was to apply Taguchi's design of experiments to optimize four key reclaimed sand parameters, namely sand strength, mold hardness, grain fineness, and moisture content to minimize casting defects while improving the tensile, strength, and hardness of aluminum alloy pulleys.
Now, I'll explain about the methodology overview used in this article. First, reclaimed foundry sand was cleaned, dried, and mixed with new silica sand, foreign resin, and additives to prepare the molding sand. Then, a wooden pattern was used to produce the mold for the aluminium alloy 390 pulley. Next, the Taguchi L9 design of experiments was applied to optimize forecasting parameters such as resin content, mold hardness, grain fitness number, and moisture content. After preparing the molds, aluminium alloy 390 scrap was melted to 700 to 720 degrees Celsius, poured into the molds, and finally allowed to cool. The cast samples were then tested for tensile strength and hardness. The results were analyzed using the signal to noise ratio and ANOVA, followed by a confirmation test to verify the optimal casting parameters. Next, let's see the key findings and conclusions of the article. First, the reclaimed foundry sand showed a higher clay content and lower permeability than the fresh silica sand due to repeated recycling. It was also found that poor control of casting parameters can lead to defects such as porosity, blowholes, sand inclusions, and shrinkage cavities. Based on the ANOVA analysis, the most significant factors affecting casting qualities were reclaimed sand strength, mold hardness, moisture content, and grain fineness number. By optimizing these parameters, the tensile strength increases to 386.4 megapascals and the hardness reached 63.58 Vickers hardness number. Overall, the study concluded that reclaimed foundry sand can effectively replace fresh silica sand, reducing production costs and industrial waste while maintaining good casting quality.
Moving on to the next section of our critique, where we evaluate the clarity and precision of the research question. Overall, our group found that the authors formulated a highly focused and unambiguous research question, which centers on how variations in reclaimed sand parameters directly affect the mechanical properties and defect rates of aluminum alloy castings. This research question has three main strengths. First, all input and output variables are clearly defined using standard engineering units such as grams per square centimeter for sand strength, AFS for grain fineness, and megapascals for tensile strength. Second, it holds strong practical relevance by targeting both foundry waste reduction and scrap minimization. Third, the questions logically aligns with the choice of statistical tools, specifically Taguchi's design of experiments and ANOVA. However, as an area for improvement, the research question could have been broadened. Instead of analyzing the reclaimed sand mixture in isolation, the authors should have included a direct comparisons against a control group of 100% fresh silica sand under this exact same experimental layout.
Moving on to the methodology. Was it appropriate for the question asked? Broadly, yes, but with real gaps. The strongest choice was the Taguchi L9 orthogonal array. Four factors at 3 level would normally demand 81 runs. The L9 bring that down to 9 while still ranking every factor. The analysis chains follow accepted practice too, as slash and ratios, ANOVA, then a confirmation run to verify the prediction. That last step is often skipped in weaker DOE papers, so its inclusion count in the author favor. All testing use standard AFS, UTM, and Rockwell method, so the work is repeatable. Three limitation though. The authors themselves call permeability and pouring temperature influential, yet excluded both from the DOE. An L9 design assumes factors act independently, so interaction like moisture and mold hardness which both govern gas escape, cannot be detected. And with only 6 casting and defect judged by eye rather than X-ray, internal porosity could never have been seen. So the very defect this study set out to control. Are the result valid? The physical trend are angular grain and residual binder do explain the lower permeability and harder mold, and the ANOVA quantify each factor cleanly. The interpretation is where it breaks down. The S/N table rank mold hardness last. The ANOVA rank it second. Both cannot be true. The abstract and discussion also give different optimum settings. Most damaging is the scale. Tensile strength rose about 2%, while the paper's own prediction error is 9.34%. The uncertainty exceeds the effect. At Rockwell readings level, VHN and a sample 8 discussed when only 6 pulleys were cast, and the claim that reclaimed sand can replace fresh silica reached well past one alloy and one geometry.
Hi, my name is Aizatu Zahira. You can call me Aiza. We're moving on to the limitation. First, the paper contains ambiguity in its binder system, confusing green and sand properties with furan resins. Second, we identify a Taguchi DOE error where the wrong formula was used for surface roughness SN ratios. Finally, testing was restricted to a single pulley geometry and alloy 390, limiting broader applications. So we're turning to the research impact. This study delivers clear practical value by directly addressing spent foundry sand, a major industrial waste stream, by validating a sand blend containing 52.2% reclaimed sands. The authors demonstrate that foundries can cut raw material consumption and landfill waste while still achieving high mechanical performance with tensile strength up to 251 MPa. Furthermore, through ANOVA statistical analysis, this study pinpoints reclaimed sand strength and mold hardness as the two dominant process parameters, contributing over 35% and 33% respectively to casting quality. Identifying this key factor gives foundry engineers a clear framework to systematically mitigate critical defects such as gas porosity, shrinkage cavities, and blowholes, ultimately driving down scrap rates and rework costs in industrial production. Finally, looking at ethical and environmental factors, during high temperature casting at 700 to 720 degrees Celsius, thermal breakdown releases toxic VSCs like formaldehyde and benzene. However, the study lacks documented safety protocol such as proper ventilation and operator PPE. Furthermore, while standard academic ethics were satisfied, the calculation errors we identified emphasize a critical need for data integrity and thorough verification before this result can be safely used in industrial applications.
Hello, my name is Shahmi bin Shahril. To wrap up our critique, we arrived at three main conclusions. First, on industrial value, the study shows that reusing spent foundry sand is genuinely viable. By reclaiming over half the sand mixture, foundries can cut raw material costs and reduce the amount of waste sand sent to landfill, which is a real win for the industry. Second, on safety and environment, while sand reclamation supports sustainability, it isn't without concerns. The furan resin binder releases harmful fumes when it burns during pouring, and the paper doesn't document any ventilation or fume extraction measures, which is something future studies need to address. And finally, our overall verdict. We rate this as a moderate scientific contribution. It offers a good initial framework for reusing reclaimed sand in aluminum casting, but it contains too many internal inconsistencies, like conflicting optimal parameter values and contradictory statistical rankings, to be considered a fully verified model. So while the direction is promising, the findings should be treated as preliminary rather than conclusive. That is all from me, and that is all from my group. Thank you everyone for listening.